Hi there, I'm Heath. This is Math 3134, the Introduction to Graph Theory. We're going to cover some definitions in this video. First definition is, what is a graph? Formally, a graph consists of two sets, a set of points that we call vertices, and the set of unordered pairs of vertices that we call edges. So this would be an example of a graph. The set of vertices is the letters A through H. The edges are edges from A to D, A to E, B to C, so on and so forth. Because they're unordered, having an edge from B to C is the same thing as having an edge from C to B. The order doesn't matter. These are the same edge, so we don't have to list it twice. Informally, though, we rarely think of the listing of vertices and the listing of edges. Instead, we come up with a visual representation that has the same set of vertices and the same set of edges. And so the graph from the previous example could be represented using this representation here. But this representation isn't unique. I could place the points wherever I want to. I can place the edges between the points. I can make them all curved, or I can make them all straight. I can choose how I want to represent things. This is entirely a stylistic choice. The definition of graph doesn't require any particular placement, and so the example from the first slide could have been presented this way, and this is the same graph as the example in the previous slide. Here's another example. I'm going to let G be the graph whose vertex set is A, B, C, D, and the edge set has an edge from A to A. We call this a loop. An edge from A to B and an edge from A to C. And so we have the edge that goes from A back to itself, the edge from A to B, the edge from A to C. And poor D is just sitting over here without any edges at all connecting to it. D is practicing social isolation. For brevity, we're going to write these edges as just a pair of letters. We won't write the curly brackets and the comma. We'll usually just write it as AB. We say that a graph is simple if no edge connects a vertex to itself. That kind of edge is called a loop. We saw one in a previous example. A simple graph is a graph with no loops. If AB is an edge in G, then we say that the vertices are adjacent, and we write this notation to indicate that the vertices are adjacent. And when we talk about the degree of a vertex, it's the number of vertices that are adjacent to that vertex. We'll see an example. In this graph, the degree of every vertex is indicated in the slide. This vertex has a degree of 1 because there's only one vertex that's adjacent to it. This vertex has a degree of 3 because there are 3 different edges coming out of it. There are 3 vertices that are adjacent to it. This vertex has a degree of 2, and so on and so forth. A graph is complete if every pair of vertices has an edge connecting that pair of vertices. We use the symbol capital K with the subscript to denote a complete graph with n vertices. Here are some examples. K2 has only 2 vertices, but there's an edge connecting them. K3 has 3 vertices, and there's an edge connecting all 3 pairs of vertices. K4 has 4 vertices, and not only are there edges along the outside, but there are the diagonals as well, because every pair of vertices has edges. What would K5 look like? We'd have 5 vertices, and every vertex is connected to itself. Every vertex is connected to every other vertex. And so all the interior diagonals have to be drawn as well. That's what K5 looks like. A walk in a graph is a sequence of vertices from vertex 1 through vertex n, so that every vertex is adjacent to the vertex that follows it in the sequence. A graph is connected if there is a walk from any vertex to any other vertex. For example, this graph is connected. I can walk from any vertex to any other vertex. As an example, the sequence A followed by D followed by C followed by E is a walk that goes from A to E. The component in a graph is the largest connected subgraph that contains some vertex. So this graph is not connected. If I think of this as a single graph, it's not a connected graph. B lies in this component, and G lies in this other component. The component is a connected piece that contains that vertex. So the component that contains B also contains A, D, and C, but it doesn't contain E, F, and G. If I have a graph and I want to delete an edge, I can do that. I can delete any edge from the graph. I just have the graph that has just one fewer edge. But if I want to delete a vertex from a graph, I have to not only delete the vertex, but I also have to delete all of the edges that connect to that vertex. For example, if this is my graph, and I want to delete vertex C, not only do I delete C, but then I have these two edges that don't have a vertex to connect to, so I have to get rid of those two edges as well. And what I'm left with, I'm not just deleting C, but I'm deleting the edges AC and BC also. I delete any edges that include C. Now, last definition. Two graphs are isomorphic if we can form a bijection from the set of vertices in the first graph to the set of vertices in the second graph that satisfies this condition. VW is an edge in this graph if the image of V and the image of W are connected, they form an edge in the second graph H. Informally, two graphs are isomorphic if there is no structural difference between the graphs. The only difference is how they're represented and how the vertices are named. As an example, these two graphs are isomorphic. In fact, both graphs are K4. This has 4 vertices, and there's an edge between every pair of vertices. This also has 4 vertices, and there's an edge between every pair of vertices. It's drawn differently, but structurally, every vertex is connected to every other vertex, just like they are in this graph. There's no structural difference between these two graphs. And so we say that they're isomorphic. In the next video, we're going to look at isomorphism much more carefully. But for today, we're going to end with a couple of theorems. First one is called Euler's Handshaking lemma. For any simple graph G with a vertex set V and an edge set E, the sum of all of the degrees is equal to 2 times the number of edges. The sum of the degrees is equal to 2 times the number of edges. And as a result of that, for any simple graph, the number of vertices with odd degree has to be an even number. Let's look at an example, and then we'll talk about how we would prove this theorem. We've seen this example before. This is a simple graph because there are no loops. If I take the sum of the degrees, that's 3 plus 1 plus 3 plus 3 plus 2. And that adds up to 12. If I count the number of edges, there are 1, 2, 3, 4, 5, 6 edges. And so the sum of the degrees does equal 2 times the number of edges. But here's why that's true. When I count the degrees, this degree includes edges 1, 3, and 5. This degree includes edge 6. This degree includes edges 4, 5, and 6. But I've already counted 5 up here, and I already counted 6 up here. This degree includes edges 2, 3, and 4, but I already counted 3 and I already counted 4. And then this degree includes edges 1 and 2, but I already counted those edges. Every edge got counted at each of its 2 endpoints. And so that's why the handshaking lemma works, is that if we add up the degree, we're counting every edge at both endpoints. That's also why we need a graph to be simple, is so that when we sum the degrees, we get edges at 2 different endpoints and not edges that have the same endpoint on both sides. And in order for this sum to be an even number, the number of odd entries has to be even, because if there were an odd number of odd entries in this list, the total would be odd. And so I have 4 vertices with an odd degree. So the number of vertices that are odd is even. All right. Thanks for watching. I'll see you at the next video.